Now, obviously, if you're dealing with a, a bunch of matter, for example, if you have a beaker full of carbon or sulfur or something else, you're probably not going to have exactly a mole, but you can figure out how many particles you have or what fraction or number of moles you have. And to do this, use the conversion factor of 1 mole over 6.02 times 10 to the 23rd particles. So this is basically telling you that if you have a mole, that's how many particles you have. And then you can also invert this. And I'll show you what I mean if we want to figure out, for example, how many moles are in 2.5 times 10. How many moles do we have if we have 2.5 times 10 to the 23 atoms of gold? So this is, if you again remember way back from the very beginning this semester when we talked about doing conversions, this is essentially a conversion problem. So the first thing we're going to do is write down the number we're given in the problem. We have 2.5 times 10 to the 23rd atoms of gold. We know that's how many we have, and we're trying to figure out the moles. So basically, like all conversion problems, then we're going to multiply by the ratio. How do we know which one we need? Do we need 1 mole over 6.02 times 10 to the 20 times 10 to the 23rd particles, or do we need particles on top? Well, what I always do is I make sure to write my units and then make sure that they cancel. So if we have mole on top and atoms on the bottom for our conversion factor, atoms will cancel and we'll end up with moles, and the question is asking how many moles. That's what we want. So this is the way we're going to set up the problem. And there's atoms canceling, and then basically we divide 2.5 times 10 to the 23rd times 6.02 times 10 to the 23rd, and the 10 to the 23rd is also going to cancel, so it's essentially equal to 2.5 divided by 6.02, and that turns out to be 0.41 moles of gold. So let's do a different problem. This time it's asking how many atoms are in 1.6 moles of calcium. So this is it's a conversion problem, but going in the opposite direction. So again, the first thing I do when solving a problem like this is to write down what I'm given. So it's like 1.6 moles. So I'm going to write that down first. And then I'm going to write my conversion factor. And again, I always write my units to figure out how to set this up. So we have moles on top is what we're given, and it's asking how many atoms. So we want to be able to solve for atoms, and we want moles to cancel. So we're going to use the conversion factor. Particles per mole. And notice here that I wrote atoms per mole because it is atoms. I could have written particles here. They're interchangeable, but in this particular case, the particle is an atom, so that's why that's written here. And then we cross out moles, so the moles cancels. And then when we multiply, then we basically multiply 1.6 times 6.02 times 10 to the 23rd. So that's 9.6 times 10 to the 23rd atoms. So if we have 1.6 moles of calcium, we're going to have 9.6 times 10 to the 23rd atoms of calcium. And in fact, this would work for anything. So if you have 1.6 moles of anything, we're going to have 9.6 times 10 to the 23rd particles of that substance. The number 6.022 times 10 to the 23rd is sometimes called Avogadro's number. It's named after a scientist named Amadeo Avogadro, who in 1811 first noticed that there is a relationship between the number of atoms in the molecule and molecular mass. So how did we come up with this weird number, which is the exact value of Avogadro's number is shown on the right. It's 6.02214173330, and the 30 is in parentheses because that's a estimate times 10 to the 23rd. So this is a pretty bizarre number, and the reason that scientists decided to use this number is that 1 mole is the number of atoms in 12 grams of carbon-12. This is an atom of carbon-12 here, the nucleus of a carbon-12. And remember, carbon 12 is an isotope of carbon that's got 12 nuclear particles. Carbon has a atomic number of 6, which means it has 6 protons, and 6 plus 6 is 12, so it also has 6 neutrons. So if we look at this nucleus, the mass of each nuclear particle in the nucleus is 1/12 of that of carbon 12. And looking again at the top, 1 mole is the number of atoms in 12 grams of carbon 12. So basically, the mass of a particle, a nuclear particle, which is a proton or neutron, is 1/12 of that. In other words, 1 mole of protons or 1 mole of neutrons has a mass of 1 gram. Um, so basically, what this means is that 1 mole of any kind of atom equals its atomic mass in grams. For example, if we have 1 mole of hydrogen, um, its mass is 1.01 gram because it's got one proton in its nucleus. And it's not exactly one because there's some other isotopes. If we have 1 mole of helium, it's got a mass of 4 grams because there's 4 particles in its nucleus, 2 neutrons. For carbon, we have there's 12 subatomic particles in the nucleus, 6 protons and 6 neutrons about. So it's got a mass of 12.01, and again, this is slightly larger than 12 because we do have some carbon 13 and carbon 14, but it's about 12 grams. In each case, though, we have 6.02 times 10 to the 23rd atoms. So if we have 1 mole of hydrogen, we have 6.02 times 10 to the 23rd atoms. That's 1 gram. We have the same exact number of atoms if we have 1 mole of helium, but it's got 4 times the mass because the nucleus has 4 times as much mass in it. And if we have carbon, again, it's the same number of atoms, but it's got 12 times the mass because there's 12 particles. So the reason we have this definition of the moles is it's very useful. It's directly related to the number of subatomic particles in the nucleus. We will now define molar mass, which is the mass of 1 mole of an atom or molecule or formula unit. For an atom, the molar mass is equal to the atomic mass, but has units of grams per mole. So for example, helium has an atomic mass of 4 atomic mass units. So if we have 1 helium atom, that's how much it weighs in atomic mass units. The molar mass is 4 grams in a mole. So if we have 1 mole of helium, that's going to have a mass of 4 grams. For neon, we have an atomic mass. We can look it up on the periodic table. It's 20.2 atomic mass units. And the molar mass is going to be 20.2 grams per mole. So they're basically exactly the same, but we're talking about 6.022 times 10 to the 23rd atoms is 20.2 grams. If we have 1 atom, it's 20.2 atomic mass unit. Because of the way mole is defined, we can do conversions between mole and mass. To do so, we need to use molar mass as conversion factor. And like all conversion factors, it can be converted to a ratio of moles per atomic mass in grams or atomic mass per mole. So let's look at an example where we want to find out how many moles there are in 36 grams of gold. So like all conversions, the first thing we need to do is write down the number we're given, 36 grams, and then we're going to figure out how to turn that into moles. To do so, we need the molar mass conversion factor, which has moles in relationship to atomic mass. Now, the atomic mass in this case is going to vary depending on what substance you're looking at, which atom you're looking at. So in this case, we're looking at gold. which has, if you look at the periodic table, it's 197 atomic mass units is the atomic mass, which is the same. So that would be the mass of one gold atom. If we have a gram of gold atoms, that's or a mole of gold atoms, that's 197 grams. So in the case of molar conversion factors, the atomic mass, you just look it up on the periodic table, and whichever element you look up, it's going to be the mass for that element. So 197 grams per mole is the conversion factor. But as always is the case in conversion factors, we have to arrange it so that we have our the units that we don't want cancel out, and the unit that we want to end up with to end up in this case on top. So how many moles? That's what we want. That's going to be on top. Grams is going to cancel, and then we do the math. It turns out that if we have 36 grams of gold, we have 0.18 moles. So this makes sense because if we had 1 mole, we'd have 197 grams. If we have 36 grams, we're going to have quite a bit less than a mole. So that seems to make sense. It's always good to check your answer and see if it makes sense, as always with chemistry problems. All right, so let's do another one. And this one, it's how many grams of calcium is in 1.6 moles. So this is a problem where we're going in the opposite direction. So we can look up the atomic mass of calcium on the periodic table. It's 40.1. So if we had 1 calcium atom, it'd be 40.1 atomic mass units. If we have 1 mole of calcium atoms, that's 40.1 grams. So the next thing we do is we write down what we're given, 1.6 moles, and then we figure out how to write the conversion so the units we don't want cancel, and the units we do want, we end up with an answer. And so that would be 40.1 grams per mole. Moles cancels. And if the answer is that if we have 1.6 moles of calcium, that is going to have a mass of 64 grams. Okay, so we not only can have moles of atoms, remember that a mole, just like a dozen, can be used for any particle. So we can use we can also have moles of molecules. Now, as I just mentioned in the previous slide, for atoms, the molar mass is going to equal the atomic mass. But instead of having the units, atomic mass units, we use the units grams per mole. So if you just look up the atomic mass on the periodic table and use units grams per mole, that is the molar mass. Now, for example, oxygen, if you look up on the periodic table, has an atomic mass of 16 atomic mass units. The molar mass is 16 grams per mole. Now, with molecules and formula units, the molar mass is going to equal to the formula mass in grams per moles. So just as we can interconvert atomic mass units to grams per moles, we can do the same thing with formula mass. So O2, that's a diatomic molecule, 2 oxygens linked together. So that's going to have a formula mass of 16 times 2, or 32. So the molar mass of the oxygen molecule is 32 grams per mole, or twice as much as that as of an oxygen atom. So we already learned that moles can be used to count particles, but they can also be used to count components of that particle. Consider the diatomic molecule oxygen, which has 2 oxygen atoms in it. So the question is, we have 1 mole of oxygen, O2. How many moles of oxygen atoms does it contain? Well, there's 2 moles of oxygen atoms for each oxygen mole of oxygen. So that would be 2. There's like twice as many. And we can also ask how many atoms of oxygen are in 1 mole of O2. Now, to do this, we need to use Avogadro's number.